Okay, should we start?
Yes.
Okay, so hello everyone. Today we are very happy to have Sanaz Pooya from Mathematical Institute of Polish Academy of Sciences to talk us about higher Kazhdan projections, L²-Betti numbers, and the Coarse Baum-Connes conjecture. Let us welcome.
Thanks a lot, Hank, and thanks to the organizers actually for the invitations and this opportunity to present my work here. It is really an honor to speak in this seminar. So as my title suggests, I'm going to introduce a generalization of the notion of Kazhdan projections and apply them to the context of Coarse Baum-Connes conjecture. In this regard, the plan for my talk will be basically start by recalling the definition of Kazhdan property T and some of its generalization, and then move on to our notion or definition of higher Kazhdan projections, then apply them to a very natural setting, and then we see there how they connect to several conjectures. And then I will show you the main application, namely to the context of Coarse Baum-Connes conjectures. And I will end my talk with a question on this context. So let's get started. Kazhdan introduced this property for locally compact groups when he was studying when he was looking for as a tool to show that a large class of higher lattices are finitely generated. So this notion was introduced in the mid-60s, and since then it became one of the fundamental notions in mathematics that has been used in various areas, not only in group theory, but also in representation theory, in operator algebras, in smooth dynamics, combinatorics, among others. So here is the definition. I guess if I got it right, this is the original definition of Kazhdan. So we say a group G has Kazhdan's property T if any unitary representation of a G, which has almost invariant vectors, it contains a non-zero invariant vector. A typical example of such groups is SL and Z when n is greater than 2. And since this notion was introduced, it has seen various characterizations. So the one that I want to present it here is the one that it's known as the cohomological characterization of property T, and it is due to Delorme-Guichardet. So the characterization goes as follows. So G has property T if and only if the first group cohomology is reduced for any unitary representation pi of G, where reduced means that the first co-boundaries are closed in first co-cycles. Now, the second part of the characterization is basically when the first cohomology group vanishes for all unitary representations. So, in the presence of first degree cohomology, one is tempted to think of like what about higher degree cohomologies? And in fact, this notion has been developed to higher degrees, and it appeared very naturally. For instance, Bader and Nowak set the first part of this characterization as a base for their generalization, and they introduce property Tn, and a group has this property if the n+1 group cohomology is reduced for any unitary representation. This appeared when, or was introduced when they were studying cohomology of deformations. Another characterization, another generalization, is due to the chiffre Glebsky, Lubotsky, and Tom, where they set as a base the second point here as a base for the generalization. So a group is called n Kazhdan if the nth degree cohomology vanishes for all unitary representation pi of G. This notion was introduced when they were studying basically approximating groups with asymptotic homomorphisms into UN, the unitary matrices of size n. So while these, as we saw by the theorem of Delong-Richardet, are equivalent in the first degree, this is not the case when one moves on to higher degrees. Obviously, vanishing implies reducedness, but the other way around is not always the case. Example, take a lattice in PGLN plus 1 QP, where n is bigger or equal than 2, and P is sufficiently large. Daimara Januszewicz showed that Hn of gamma for any unitary representation with respect to any unitary representation is reduced, but it is not always vanishing. And in fact, there is one representation that one can take, and that is going to be a witness for this non-vanishing. So we will come back to this example later. Now, I would like to mention next yet another generalization of, or first characterization of property T that has been used a lot in C-star algebraic context, and in particular, it proved useful in the context of the Baum-Connes conjecture. So this characterization is in terms of existence of a certain projection inside maximal group C-star algebra of G, whose image under any unitary representation of G is the orthogonal projection onto the fixed vectors of pi. This projection is known as the Kazhdan projection, and I would like to make a few remarks about this. So first, this is non-zero inside C star max of G, and this is witnessed by the trivial representation. Next, if one starts with an infinite group G, this projection always vanishes inside C star reduced of G, because the left regular representation does not have any fixed vectors except for the trivial one, as soon as we are working with infinite groups. So basically the tension between these two phenomena violates certain methods of proof for the Baum-Connes conjecture. Basically those methods that would right away implies isomorphism for the usual Baum-Connes assembly map, namely the one to the K-theory of reduced group C-star algebra, and the maximal one, the assembly map into the K-theory of reduced group C-star algebra. Because we have one projection that is 0 and is mapped via lambda, which is non-zero and mapped via lambda to a 0 projection. Nevertheless, Baum-Connes has been proved for some property T groups via modifications of these proofs. So now, basically, motivated by this phenomena and aiming to provide more counterexamples to the Baum-Connes conjecture, in particular to the Coarse Baum-Connes conjecture, because there are counterexamples coming from property T, and now we would like to see if one moves to higher degree, whether we can still produce counterexamples. We introduce a generalization of notion of higher notion of Kazhdan projections in higher degrees. So before I give you the definition, I would like to quickly go over some basics in order to fix my my notations. So we start with the group G with property T. This group is finitely generated. Let's fix the set of generator by S. We fix a unitary representation pi of G. And we keep in mind that the Kazhdan projection viewed inside this representation is the one into the pi G fixed vectors of pi G fixed vectors. So the idea is basically to try to understand or describe fixed vectors or the image of this projection in such a way that it allows generalization to higher degrees. So this motivates us to look into the Markov operator, the averaging operator over the generators, whose invariance contains all information about the invariance of pi of G. Now, if you take the Laplace operator, namely the operator 1 minus Markov operator, which still lies inside the group ring, then we see immediately that the kernel of Laplace operator is the invariant vectors of pi. One last remark on this is that we can further identify this the set of invariant vectors with the 0th degree cohomology, because these are always the 0th degree cohomology gives us the invariant vector. Okay, now let's move to higher degrees. We fixed the representation, and we have seen that we basically have this equality. I put 0 here just to see that basically what we are going to generalize. So further, let's assume that G is a group of type of infinity. This is going to just simplify our construction. But as we will see later, we don't need to work with group of type infinity. And type infinity means that there is a model for the classifying space of G who has finite number of cells in each degree. Okay, so take the field resolution associated to this model for the trivial ZG modules Z. So we get by standard such a resolution where the number of direct sums corresponds to the number of cells in each degrees. Now we apply Hom functor, and then we get a cochain complex where we can identify terms by a number of direct sums of Hilbert spaces. This index is the same as what we had before here, and then we get a cochain complex in this form. Just maybe a remark that I did not put the connecting maps here, or I did not introduce them, but just maybe one thing to keep in mind is that these connecting maps lives inside matrices over the group ring, and then when we move here inside matrices on with the values here. Very good. So now the Laplace operator, the classic Laplace operator, can be viewed as the adjoint of this codifferential times its the codifferential in 0 degree, which acts on H, and then ends Laplacian is when one takes basically the sum of these two codifferentials, the 1, 2, and the one out from this, once we take the correct adjoint to have them all land inside or act on this Hilbert space. So what we want to see was something like this. Obviously, we have to forget about invariant vectors, but in fact, the equality between the kernel of Laplacian and the first 0 degree cohomology can be seen and can via this Kazhdan isomorphism, which in fact provides us with the similar phenomena, namely the kernel of delta n viewed inside pi is isomorphic to the nth degree reduced cohomology of G with coefficient in the representation we fixed from the beginning. Now with this, we can actually define higher Kazhdan projections. So we get a group G and we fix the unitary representation of G. The higher Kazhdan projection in degree n associated with this unitary representation is the orthogonal projection defined on the nth cochain into the kernel of pi delta n. So this projection lives always inside the matrices over the von Neumann algebra generated by pi g. But maybe the interesting case interesting situation for us is when we can view actually this projection inside the C-star algebra, because then we can study K theory and find the connection to K theory of various C-star algebra, wherever this projection lands. So in this case, we assume spectral gap, and this will produce an element inside the matrices over the C-star algebra generated by pi g. And as such, this is in fact the heat semi-group projection that we have seen that has appeared naturally in other contexts. Okay, so now I would like to introduce one more basically ingredients in order to be able to compute this Kazhdan projection and apply it to some natural settings. So this piece of ingredient is going to be L²-Betti number. So recall a group von Neumann algebra of G is just a strong strong operator topology closure of the group ring inside bounded operators on L2 of G. This comes always with a canonical trace, which associate to finite sums of elements inside the group ring the coefficients for the coefficients of the identity. Now, nth L²-Betti number of a group G is defined as the von Neumann dimension of this module, namely the nth reduced cohomology of G with coefficient into L2 of G. And as such, this always lies inside this interval. If we have a finitely generated module, then of course this is it's a finite number, but otherwise it can attain infinity. Now, using the classification of finitely generated right von Neumann module, we see that they all fit in this this picture. So there is a projection basically satisfying this. And in the specific situation, when our finitely generated module is the nth degree cohomology with this coefficient, then the projection fitting in this setting is the Kazhdan projection, the higher Kazhdan projection. And this can be seen through the theorem isomorphism that we had before. So now one standard line of identification, we see that the nth L²-Betti number of a group G is the value that the trace tensor, the canonical trace, would associate to this projection. So by trace, I mean the matricial trace. Now, a situation where this setting actually fits quite naturally is that when we assume that we have spectral gap such that this Pn belongs to matrices over the reduced group C-star algebra, then obviously we have this equality that the trace, the von Neumann trace extended to the K theory level at the K theory class of Kazhdan projection equals the nth Betti number of L²-Betti number of the group G. In particular, if we know that the nth L²-Betti number is non-zero, then we get a non-zero projection inside K theory of C-star reduced of G. And this is in fact interesting because in the classical setting, of course, this projection would always vanish. But when one moves to a higher degree, this phenomena does not appear necessarily always. So viewing it in this way, in the presence of the values of the canonical trace. And Betti numbers, there are two settings where one can actually fit this setting. One is the trace conjecture, and the other one, as we will see, is the Atiyah conjecture. So let's start with the trace conjecture. So the modified trace conjecture formulated by Wolfgang Lück says that for any group G, the image of the canonical trace on the K-theory of reduced group C star algebra of G lies inside the ring generated by the inverses of the finite subgroups of G. And if we assume further that the Baum-Connes assembly map is surjective, this conjecture is a theorem. So it always holds. So this tells us that these Betti numbers must be a rational number. And maybe a remark on the word modified trace conjecture that I would like to make here is that, in fact, Baum-Connes conjectured in the original article that such values would lie inside the group generated by these numbers. It turns out that there is a counterexample to that, and in fact, I think Roy constructed a counterexample where she has a group such that the order of finite groups are either trivial or 3, and then there is an element living on the left-hand side of the Baum-Connes assembly map, whose image under the trace and the assembly map would be something like 1105 divided by 9. What is important about this is that this number is not an integer when one multiplied by 3. So so one sees that the denominator 9 appears in this setting, and then afterwards Lück modify that and correct it to this setting where one takes basically, instead of the group generated by this, a ring generated by this. And this obviously covers the counterexample that Roy had. Okay, so right. So as I said, this the combination of this plus what we have as the value that this trace can attain, one gets that under surjectivity of the Baum-Connes assembly map, this L²-Betti number must be a rational number. And if G is torsion free, then these are integers. All right, now let's move on to the other picture, namely the Atiyah conjecture. So first, maybe a little bit of history. So when Atiyah introduced L²-Betti numbers for compact manifolds, he asked what kind of numbers this value can attain. And in particular, he asked whether these are always rational, and or if the fundamental group is torsion-free, these are integers. So since then, this question has seen several form of basically generalization, and one strong one, which is still an open question, is that it is what Lück and Schick formulated as the strong Atiyah conjecture, the bounded version, which reads as follows. So we start with the group G with a bound on the order of finite subgroups. Hence this, the adjective bounded comes in. Then for any n inside natural numbers and any operators inside matrices over the group ring, the von Neumann dimension of the kernel of T lies inside the group generated by these inverses. So in fact, from such an operator, one can take the kernel and then associate it to that and a kernel projection, and then this dimension would just says what is the value of this of the matricial trace tensor with the von Neumann trace on this projection. And this is it is conjectured that this lies inside the group generated by this. And it is a rational number. So obviously, if one finds an irrational number, then one basically has counterexample for all these conjectures. All right. Now we have seen that this the notion of higher Kazhdan fits naturally in the setting of conjecture and the Baum-Connes conjecture and related conjectures to that. Maybe one question one asks is, after all, what kind of projections these are? What could they be? I mean, are they always trivial projections, or can they be actually non-trivial? We said that they can be non-zero, but the question remains whether they can actually be non-multiple of the identity. So let us see some computations, and maybe before that, I would like to provide us with a tool from the work of Bader and Novak, where they say that a higher Laplacian has spectral gap if and only if the group cohomology in degree n and n+1 is reduced. So we will use this as a tool to verify that we have the spectral gap, guaranteeing that this Kazhdan projection lies inside the completion of the group ring that we want. Okay. So first example is just the basic example, the Kazhdan, the classical setting of the Kazhdan projection. So as I said, if you have an infinite group G, obviously there is no invariant vectors for the left regular representation besides 0. So this projection is always 0. Let's take a free group on n generators. We can check that first Laplacian has spectral gap using this lemma. In fact, in degree 1, it has spectral gap because this is a non-amenable group. And in degree 2 has spectral gap because if one takes as a model for this just a wedge of n circles, then one sees that there are no two cells. So the cohomology vanishes, hence it is reduced. So with this, we guarantee that this Kazhdan projection lies inside matrices over the C star reduced of Fn. What next? We know that the first L²-Betti number of free group on n generator is n-1. And we know that the K-theory of C star reduced of Fn is Z generated by the identity. Putting all this together, we can identify the class of Kazhdan projection as a multiple of the identity. So next, now let's take SL2Z. This is basically free group on two generators. So more or less for the same reason as above, we get spectral gap for the first Laplacian. But here, the first L²-Betti number of SL2Z is 1/12, which then tells us that the value that the trace would attain on this projection is 1/12. This, and we know further that the K-theory of C star reduced of SL2Z is Z28. So this tells us that actually this projection is not a multiple of the identity. Last example. Let's take a lattice inside PGL3 QP with the assumption, as I mentioned before. One can show that P2 lives inside matrices over the C star max of G, and it is non-zero. Well, again, with what I said at the beginning of my talk, in this case, the cohomology is reduced always. So we get this basically by the result. And then the fact that this is non-zero can be seen through the existence of one unitary representation that comes as coefficient and witnesses this non-vanishing. So this says that this projection is non-zero. So we can produce this, or we can view this projection inside various C star algebras. Okay. So with this, I would like to move to the context of Coarse Baum-Connes conjecture and mention the basically main application of this projection to that context. So like we start with the standard assumption, namely X is a discrete metric space with bounded geometry. We have a separable infinite dimensional Hilbert space, C of X inside bounded operators on L2 of X with comma H would be just a star algebra of finite propagation operators with compact entries. With this, I mean that one can always view elements inside these bounded operators on this Hilbert space as just a matrices, let's say T, and then the entries would be T, X, Y, and finite propagation means basically there is a band around the diagonal of this matrix where the elements or the entries, these operators can be non-zero, but anything outside this would be zero. Now, the row algebra of X is just the closure of this star algebra inside these bounded operators. And Coarse Baum-Connes conjecture is a statement about the K-theory of the row algebra. It was formulated by Rowe in 93. And it goes as follows, that for X with bounded geometry, this assembly map is an isomorphism. So the left-hand side can be defined via direct limit, but now I just put it in this way. So maybe 2 points to make here is that this version of Baum-Connes does have counterexamples, but it also has lots of confirmed cases. So one class of counterexamples are coming from groups with property T and then expander graphs. And I think you Willett showed that expander graphs with large gers do not satisfy surjectivity of the coarse assembly map. On the other hand, among these confirmed cases is a result by Goliang Yu, which says that those metric spaces with bounded geometry that can be coarsely embedded into Hilbert space satisfy the conjecture. Now, let's see how our Kazhdan projections actually can be applied to this setting. So here's a theorem. I think I forgot to mention that this is based on joint work with Conley and Piotr Nowak. So here our theorem goes as follows. So we start with an exact residually finite group of type Fn+1. So type Fn+1, I mentioned it just means that in n skeleton we have finitely many cells for a model for the classifying space, and residually finite is just the standard assumption in this setting. and exact will be used as a tool, as we will see in the proof. Exactness will appear as a tool in the proof. So we have a residually finite group. We take a filtration. Let's denote them by ni's. And this means that we take a finite index normal subgroups of G, such that they such that this is a descending sequence of ni's, and they intersect trivially. So this is what I mean by filtration of these finite index normal subgroups. And now let's take the quasi-regular representation associated to this Ni and put them all together to make one representation here, unitary representation, where we call it pi. Now, if we assume that the pi delta n has spectral gap, which allow us to view Pn, the Kazhdan projection, inside matrices over the C star n of G, so the completion of the group ring with respect to the norm coming from this representation. Now, if we assume further that the coarse assembly map is surjective for the box space associated to this filtration, then we get this equality between L²-Betti numbers and Betti numbers of this filtration when we go far into the sequence. Box space is just a metric space associated to a group, a residually finite group, basically. So one takes the Cayley graphs of these finite groups, and then from that one looks at the disjoint union, and this will give us a box space, one metric space associated to G. So we get this as a result, this equality between L²-Betti numbers and Betti numbers, and I would like to remind us that in fact Betti numbers are just a dimension of group cohomology with coefficient in C, and this always lies inside natural numbers, while as we saw, L²-Betti numbers defined in this way always lies inside this interval. So this theorem with this assumption forces the L²-Betti numbers actually to be a natural number. And obviously, if we find a group with these properties, and then we get two different values in the limit for L²-Betti numbers and Betti numbers, then we have a counterexample to this conjecture through this cohomological approach. Maybe a few words on the proof. So this proof uses the idea of Hickson's original result on counterexamples for a Coarse Baum-Connes conjecture, which then developed further by Willett and Yu. So we have this diagram here. So on this part, we see the coarse assembly map for the box space associated to the filtration. So Y is denoting that. And then the idea is to provide two different traces on the image of the assembly map, which then gives us on the one hand the L²-Betti numbers, and on the other hand Betti numbers. So one trace is D star, and the other one is through lifting to this space and then combining it with a trace that exists up here. So what are these traces? So we have this Kazhdan projection inside the matrices over the C star n of G. With that, we can produce a Kazhdan projection, a high Kazhdan projection associated to uniform row algebra, and then we tensor it with rank 1 projection in order to get a projection inside the row algebra. So we have that, and then we basically look at the image of this projection inside the quasi-regular representation, or boxes if you like, and then the dimension of these boxes would then give us the Betti numbers of, would correspond to Betti numbers of ni's. And if we lift it up here and then combine it with this trace, we get the L²-Betti numbers. How do we get them? Basically, first hint is that here we have this equivariant setting that should remind us of modular structures in von Neumann algebra that we have, and then L²-Betti numbers are just natural things to get here. But besides that, one can identify these C-star algebra, equivariant C-star algebra, with the reduced group C-star algebra of Ni tensored with compact operators. And now we have two traces. So on the compact operators, we have the unbounded trace. And on the reduced group C-star algebra, we have the von Neumann trace, the canonical trace. And these are the ones that will give us the value of L²-Betti numbers. They will give us the L²-Betti numbers. And by commutativity of this diagram, we see that if something belongs to the image, then these things must be equal. And as a result, we get the equality between different Betti numbers and L²-Betti numbers. Okay, mentioning a comparison between L²-Betti numbers and Betti numbers actually, in a sense, forces us to consider happily, yet another result by Wolfgang Lück, in this case, Lück's approximation theorem, which is a statement about comparison between L²-Betti numbers and Betti numbers. So the theorem goes as follows. So if we have a residually finite group of finite type, and we have a filtration of G, and then the nth L²-Betti number of group G is just the limit of the normalized Betti number of this filtration. All right. Now, a quick recall that if we have a subgroup N inside the group G, then the nth L²-Betti number of N is related to the one of G through this index. So nth L²-Betti number of N equals the index times the nth L²-Betti number of G. So putting this together, or using this in order to translate our result to this setting, then when compared, actually, we get right away an identity instead of this limit. Okay, so in my last slide, I would like to put this setting of Kazhdan projections into the setting of what is called as high-dimensional expanders. And this is, it's going to be a little bit hand-wavy here, because this is something that I recently started to think about, but I would just like to share the idea here. So let's start by first the definition of expanders. So expander graphs are a sequence of finite connected deregular graphs, such that the number of vertices of each of these graphs tends to infinity, and there is uniform spectral gap. One can show that product of expanders is again expander. So then this basically, which then would give us like a higher complex, a high dimensional complex. And that is basically the connection to this high dimensional expander setting. So these high dimensional expanders are simplicial complexes that can be viewed as high dimensional analogs of expander graphs. There has been several approaches to actually defining this, defining them and the particular expansion. But maybe the one that fits best to our setting is the one through uniform spectral gap for the Laplacian. So in that sense, an n-dimensional spectral expander would be just a sequence of finite simplicial complexes, such that if one looks at this Laplace operator in higher degree, then there is this uniform spectral gap. So this delta I plus, so the plus refers to the situation where one only in this cochain complex that I had in my in the middle of my talk. And when we defined the higher Laplacian, we basically had the sum of the n-1 codifferential and the nth codifferentials composed with their adjoints in the right way. And in this case, the plus would just refer to the setting where we only look at the codifferential of the nth codifferential, or in this case, I codifferential. Now, in view of this, maybe a natural question to ask is that under which condition these high-dimensional expanders provide counterexample to the Coarse Baum-Connes conjecture. So there is this result of Yu and Willett, which says that expanders with large Gers do not satisfy the surjectivity. So maybe one wonders whether there is a way to basically make this work in this high-dimensional setting and provide further counterexamples to the Coarse Baum-Connes conjecture. So with this, I would like to end my talk, and thanks all of you for listening to my talk.
Thank you very much, Sanaz. So do we have any questions from the audience or comments?
I have a question.
Yes, please.
So in the slide of your main theorem, could you give an example or some examples for what kind of groups satisfy the assumptions?
For example, free groups on two generators.
Yes.
Is exact, residually finite, and then for this you can take a filtration which gives you expander graphs, say.
Yeah, sure. Are there any more sort of natural examples?
I'm sorry?
Are there any more natural examples?
What do you mean by natural examples? What would you like
some
to
of the
see?
examples that you mentioned at the beginning of your talk?
So if I have it for free group, for example, I can also show that for SL2Z if you like.
Oh, okay, yeah, I see.
But in that setting, one gets that this Kazhdan projection does not lie inside the image of the Baum-Connes. Basically, one gets a counterexample. So one can show that on the one hand, one gets Betti numbers 1, and the L²-Betti numbers would be 0. And this would guarantee that this projection does not belong to the image of the Coarse Baum-Connes.
I see. Thank you. Thank you very much.
More questions?
You know, in a way, all these counterexamples are in the same vein somehow. I mean, they are always using expanders or things of this type. I mean, what is important is that, for instance, all hyperbolic groups satisfy the conjecture. So in some sense, difficult to. I mean, what one would like to have is somehow where is the boundary between things which satisfy the conjecture. Things which it's a bit. I mean, in the case of the coarse conjecture, okay. I mean, the group has somehow disappeared. I mean, it's more the core space which is in question. So it's a different flavor. It's quite a different flavor than from the group case. I mean, yeah. So, I mean, in the group case, what remains quite open, if I understand well, is the fact that, for instance, if you have a torsion-free group, one would expect the Atiyah conjecture to be true, and so that's wide open, if I understand correctly. Yeah? Yes.
Mm-hmm.
Yeah.
Right.
Maybe another question. So is this related somehow to the Kazhdan and Kaplansky conjecture in some way, or?
Surjectivity of the Baum-Connes assembly map implies Kazhdan-Kaplansky conjecture.
I see, okay.
Yeah, there is another thing which is worth mentioning, which is that now there is a counterexample to the Kaplansky conjecture for the unit in a group ring.
Right.
Yes.
Which is quite recent, and it's very easy to check because it's and the group is of course satisfies Baum-Connes and so on, because the group is essentially abelian. I mean, it's a finite extension of an abelian group. So I mean, the group in itself is not very interesting for us. On the other hand, what is quite interesting is that the Kaplansky conjecture for the units, if you want, for the invertible elements in the group ring, it turns out to be wrong with coefficients in F2, in the finite field F2. And I mean, and the counterexample is very simple, actually, very simple to check on the computer, for instance, that it is a counterexample. But I don't think it's really quite important for us in a way. I mean, but
yeah, I guess we are interested mainly in the complex group ring.
Yeah, it's not a counterexample in the complex group ring.
Yes,
yes. A counterexample only in the with coefficient in Z2. But
in
yeah.
Do you have more questions or no? Okay, if no, let us thank Sanaz for the wonderful talk, and thank Alan for the comment.
Thank you, Sanaz.
Thank you. Thanks for listening.
See you next week.
Bye-bye.
Bye.
Bye.
Thank you. Goodbye.